guys, welcome to my YouTube channel. Today we'll be discussing utilization of ATP, a continuation from metabolism. So we are going to find out everything about ATP and its role in the two stages of biosynthesis. So the two stages of biosynthesis, we are going to have the formation of building blocks and their specific assembly into macromolecules, which are energy consuming processes and thus they require ATP. Although the ATP is derived from catabolism, catabolism does not drive biosynthesis. Okay. So, although biological growth and development result in the creation of ordered systems from less ordered ones and of complex systems from simpler ones, these events must occur at the expense of energy yielding reactions. The overall coupled reactions are, on balance, still accompanied by a decrease in free energy and thus essentially irreversible in the direction of biosynthesis. So the total energy released from ATP, for example, is usually much greater than is needed for a particular biosynthetic step. Thus, many of the reactions involved in biosynthesis release inorganic pyrophosphate rather than phosphate from ATP. And because of this, you're going to have yield of AMP rather than ADP. Since inorganic pyrophosphate readily undergoes virtually irreversible hydrolysis to two equivalents of inorganic pyrophosphate. So the creation of a new bond in the products of synthesis may be accompanied by the breaking of two high energy bonds of ATP, although in theory one might have sufficed. Okay, so when we move on to the next step, so the efficient utilization for anabolic processes of ATP and some intermediate compound formed during a catabolic reaction require the cell to have simultaneously have a value favorable for both ATP generation and consumption. So catabolism occurs readily only if sufficient ADP is available, hence the concentration of ATP is low. On the other hand, biosynthesis requires high level of ATP and consequently low levels of ADP and AMP. So suitable conditions for the simultaneous function of both processes are met in two ways. So biosynthetic reactions often take place in compartments within the cell different from those in which catabolism occurs. So there is thus a physical separation of energy requiring and energy yielding processes. So biosynthetic reactions are regulated independently of the mechanisms by which catabolism is controlled. So such independent control is made possible by the fact that catabolism and anabolic pathways are not identical. So, in contrast, you're going to have many biosynthetic routes are regulated by the concentration of the end products of particular anabolic processes so that the cell synthesizes only as much of these building blocks as it needs. So that we don't have a lot of it. So, when we come to the supply of biosynthetic precursors, we are going to have, when animals consume a mixed diet, we are going to have sufficient quantities of both compounds for both biosynthesis and energy supply available. So, carbohydrates yield intermediates of glycolysis and of the phosphogluconate pathway, which in turn yield acetyl CoA enzyme. We have lipids yield glycolytic intermediates and acetyl-CoA enzyme, and amino acids form intermediates of both the TCA cycle and glycolysis. So any intermediate withdrawn for biosynthesis can thus be rapidly replenished by the catabolism of further nutrient. So this situation, however, does not always hold. Microorganisms, in particular, can derive all of their carbon and energy requirements by utilizing a single carbon source. So, the sole carbon source may be a substance such as a carbohydrate or a fatty acid or an intermediate of the TCA cycle. So in both cases, reaction and auxiliary to those we have discussed before can be utilized. So we have the anaplerotic routes. So even though the catabolism of carbohydrates can occur through various routes, also give rise to pyruvate. During the catabolism of pyruvate, one carbon atom is lost as carbon dioxide and the remaining two form acetyl-CoA enzyme. So these two are involved in the TCA cycle. And because the TCA cycle is initiated by the condensation of acetyl coenzyme with oxaloacetate, which is regenerated in each turn of the cycle, the removal of any intermediate from the cycle would cause the cycle to stop. Yet, various essential cell components are derived from alpha oxoglutarate, succinyl coenzyme A, and oxaloacetate, so that these compounds are in fact removed from the cycle. So we are going to have microbial growth with a carbohydrate as the sole carbon source is thus possible only if a cellular process occurs that is going to affect the net formation of some TCA cycle intermediates from an intermediate of carbon.